Welcome to this explainer. So picture this. You've just booked a dream vacation to somewhere totally incredible, maybe Japan or South Korea. You settle into your seat, you tap the screen to check out the in-flight map, and you notice something completely bizarre. Instead of pointing straight across the vast Pacific Ocean, your plane is taking this massive detour way up north over Alaska. I mean, it almost feels like a mistake, doesn't it?
It really makes you wonder, why avoid a straight line? Did the pilot take a wrong turn? Did you accidentally sign up for the Caribou route? It's completely counterintuitive when you first look at it. Because, we're all taught that the shortest distance between 2 points is a straight line, right?
Now, your very first instinct is probably safety. The Pacific Ocean is this seemingly endless, bottomless pond. If an engine happens to fail at 30,000 feet, you obviously want an emergency landing spot, and Alaska, while pretty sparse, is definitely a whole lot better than sinking into the ocean. But the actual reason driving these routing decisions, it's saving time and fuel efficiency. It's easy to forget sometimes, but airlines are businesses, and their absolute top priority is moving passengers quickly and cheaply. Time and fuel are quite literally money.
Okay, let's really dive into this. Speed is usually the primary factor in determining a flight path. Excluding crazy meteorological concerns, which, don't worry, we're going to get to in just a minute, the fastest route is almost always the one closest to a straight line.
But wait, is it actually a straight line? If you glance back at that little in-flight monitor, the path looks like a massive, curving rainbow stretching all the way over Alaska and the northern Pacific. I mean, that doesn't look like a straight line at all. In fact, it looks like you're going wildly out of your way just to avoid getting your feet wet. And this right here brilliantly illustrates the core of the confusion. It's basically a battle of dimensions. On a 2D flat map, plotting a course from Los Angeles to Tokyo creates that long, curving rainbow detour. It looks terrible for fuel efficiency, but, well, we don't live on a piece of flat paper. If you take a 3D globe and pull a string tight between those two exact cities, the string doesn't run parallel to the equator. It bends upwards to trace the curve of the planet. So in three-dimensional space, that northern arc actually is the straightest, shortest path. But actually, scratch that. Even that string on a globe trick has a flaw. Because, as this quote points out, unlike a globe, the Earth isn't a perfect sphere. That beautifully smooth, perfectly round globe you bought at the bookstore, it's kind of lying to you. We need to peel back an even deeper layer of reality here. Now, here is where things get really fascinating. Look at this specific number, 24,860. If you were to take a giant piece of string and measure the Earth's circumference vertically, so right through the North and South poles, you would need exactly 24,860 miles of string. But check out the equator. If you wrap that exact same string around the middle of the Earth, the number jumps up to 24,900 miles. That's a 40-mile difference. Our planet actually has a bit of a midsection bulge.
So why does that happen? Well, the Earth bulges out because it rotates on its axis. Think back to being a kid on a playground merry-go-round. When you spin yourself really, really fast, you feel that centrifugal force kicking in, making you feel like you're going to be thrown outward to the sides. The Earth is experiencing that exact same force as it spins through space.
And that force is absolutely immense because of this number, 1,000. Anyone tuning into this explainer from the equator right now is currently moving at roughly 1,000 miles per hour. That incredible rotational speed generates enough centrifugal force to push the planet's midsection out, which creates all that extra width.
So, the crucial takeaway from our planet's wild geometry is this. Why do flight paths curve toward the poles? Well, first, the Earth is a 3D sphere, not a flat map. Second, the planet has extra equatorial width because of its spin. When you synthesize those geometric facts together, curving north over Alaska actually creates a physically shorter distance than flying what looks straight across that bulging middle on a flat map. It's honestly just brilliant applied mathematics.
Okay, so that solves the geometry puzzle, but it totally brings up a new question. Do planes ever just cross the open ocean? I mean, people still have to fly to Australia, right? Despite the giant insects and spiders. So, geometry aside, what else dictates when a plane will just say forget it and power straight over the water?
When pilots do brave the oceanic voyage, it's almost always to battle the elements. They'll intentionally steer out over open water to outclimb severe weather, like hurricanes and tropical storms. Sometimes they literally just need to avoid massive, everyday thunderstorms whose clouds can reach a staggering 60,000 feet. Heights that planes are strictly advised to steer around, definitely not over. Ultimately, braving the ocean is all about escaping severe cabin turbulence, keeping you and all your heavy luggage from getting violently tossed around. And there's another invisible meteorological secret at play here too. Water handles heat completely differently than land does. Over continental airspace, hot air is just constantly rising up from the sun-baked soil, creating a bumpy, highly turbulent ride. But oceanic airspace? Water distributes heat much better than soil does, which results in significantly smoother air. So sometimes, taking the ocean route is simply about giving passengers a much more comfortable ride.
But there is one final, completely invisible layer to our flight path puzzle, a zone called the tropopause. This is the fluctuating border between the troposphere, which is the lowest layer, where our weather actually happens, and the stratosphere right above it. It sits about 4 to 12 miles above the Earth, and it is a wildly volatile zone of incredibly rapid shifts in air temperature and pressure.
Those rapid shifts in the tropopause create literal wind tunnels in the sky. And in the winter, when the temperature differences are at their absolute most extreme, the winds in these tunnels can exceed 200 miles per hour. That is an absolutely massive amount of force.
We call these intense wind tunnels jet streams. Thanks to the Earth's rotation, they mostly flow from west to east. The two most important ones for air travel are the polar jet stream up near the Arctic Circle and the subtropical jet stream closer to the equator. They're thousands of miles long but incredibly narrow, like only a few miles wide. If a pilot can map a route to ride them perfectly, it can shave hours off your travel time. But flying into one head-on? Yeah, that will slow you to a crawl. But riding the jet stream comes with a serious warning label: clear air turbulence. This is an intensely unpredictable, nearly invisible form of turbulence that happens right along the jagged edges of those high-speed jet streams. It causes sudden, terrifying altitude drops. Back in 1997, a flight from Tokyo to Honolulu hit clear air turbulence and dropped so fast that unbuckled passengers were violently thrown from their seats. This right here is exactly why flight attendants always tell you to keep your seatbelt fastened at all times, even when that little seatbelt sign is off. So let's bring this all together. Safe, fast, and efficient air travel requires perfectly balancing three different layers of reality. You've got geometry, where the Earth's 3D curvature and bulge dictate a shorter physical path via the poles. You've got meteorology, where avoiding heat and massive storms sometimes pushes flights out over the smoother oceans. And finally, you have the atmosphere, where tapping into invisible jet streams speeds up travel from west to east. It is just a stunning balancing act every single time a commercial plane takes off.
It's really incredible how much physics, geometry, and atmospheric science goes into what feels like just a simple vacation flight. Which kind of leaves us with this fun question. When will your car need to worry about jet streams and the Earth's curvature? Well, probably not today. Unless you plan on strapping literal rockets to your bumper and traveling hundreds of miles an hour, your daily commute is completely safe from clear air turbulence. But the next time you look at that curved flight map, ask yourself this: how much of our daily lives is shaped by invisible forces we completely misunderstand, simply because we're so used to looking at them on a flat screen? Thanks for joining me to explore the hidden logic of the skies, and keep looking up.